Hello everyone, I am Dr. Satyanarayan Rao. In my last video, I actually showed how we can use random forest regression, which is a machine learning model, to predict soil moisture from satellite backscatter. I also discussed feature engineering and highlighted that sandy loam soils actually stood out by outperforming other models. Other soil textures. So after I released that video, I received some good questions from the viewers, including from Professor Sekhar Muddu about whether the sandy loam is truly special. The main concern was whether the strong performance of sandy loam was just due to some obvious reasons that is of non-scientific interest. Maybe it just happens to have more bare soil or something else very simple rather than something meaningful. So these are actually valid scientific questions, because if our results are just because of something very obvious that is actually unrelated to soil texture, then the story isn't that strong. So in this video, I will first talk about what those concerns were, and then I will walk you through how I went back and checked with the data. I split the samples and made some new plots and tried to see if these questions had any real meaning. Goal is to see whether my previous statement that I make, that sandy loam is the best performing soil for the random forest approach, will it still hold good after a closer look. And I also recommend you to watch my previous video in full, because there I go in more detail about feature engineering, the machine learning approach, and the background that you need to make sense of what I discuss in this video. So let me quickly recap what we did. We had a dataset of 677 samples in total, and that's what you see here in the first gray color bar labeled overall dataset. This is the full dataset, and we calculated the correlation, the simple correlation between the HH polarized backscatter from the satellite and the field measured soil moisture. And then I split this whole dataset into different soil texture based on USDA classification, and we computed the correlation separately for each texture. That's what you see in the brown color, different color bars. And what we see here that the red color horizontal line is the correlation for the entire dataset, which is around 0.59. That's our baseline. And now when we look at the results of the individual textures, we see that most of them, like clay, sandy clay, and sandy clay loam, actually had correlations that was actually below the overall average. Only two textures actually performed better than the average, the loamy sand and sandy loam. And among them, the sandy loam actually was the highest with 0.759. And this plot is what motivated me to later train random forest machine learning model for each soil type. And this result, actually this plot, actually drew some questions, especially from Professor Sekhar Muddu, that one key concern was, is sandy loam really that special? If the high correlation that we see is due to something more obvious like the land cover, maybe the sandy loam and loamy sand happen to have more bare soil than others, and that's why SAR tends to perform better on bare surfaces when there is no vegetation to interfere with the signal. That might be causing this high correlation. And also, sandy soils are often less irrigated and less intensively cultivated in India, because they cannot hold that much water like clay. So there will be sparse vegetations, which again could make SAR to pick up stronger signals, and that's why we see high correlation. So the worry was that the model is not really detecting the texture specific signal, but rather responding to vegetation cover. then if that's true, then the previous story that I told in my previous video might not hold strong. And that's what we wanted to test in this video. We are still in the recap. As I explained in the previous video, I trained machine learning model, the random forest, first using all data together, which I call the generic model, and then I also trained separate model for each soil texture. And we compared the R square. 1 means perfect prediction, 0 means model is no better than guessing the average, and a negative value means model is worse than that. So here in this plot we see the R square for each model. The generic model was around 0.45, but what's important is that when the model was trained on sandy loam or individual soil texture, the sandy loam gave us the highest R square of 0.6, which is around 34% improvement as compared to generic model. But in contrast, the other soil texture did not show any improvement. So in the last video, as I claimed, the texture specific calibration doesn't always help, but in the case of sandy loam, it clearly does help. That was the key message. This actually raised some concern, as we mentioned earlier. What if this improvement, the R square improvement for sandy loam, is due to vegetation and not due to soil texture? But we saw high correlation of loamy sand and sandy loam in the previous slide. But when we compare the random forest R square, it's only sandy loam that shows better result as compared to a generic model. So let's maybe these samples had less vegetation and more bare soil, which could make the machine learning model to learn better, and that's why we see high correlation. So to understand that, we will look into land cover, how much each soil texture was vegetated, how much was bare, and what was the mean leaf area index in each case. This will actually answer some of these questions. So now this plot actually already gives us some big clue about the concerns we discussed earlier. So what you are looking at here is the correlation between the backscatter and the soil moisture, but segregated by several different factors, not just soil texture. We have the overall correlation and each soil texture, and also two SAR bands, L band and C band. And also finally the land cover, bare soil versus the vegetated soil. So what we see is that when we focus on the soil texture, we can see that the loamy sand and sandy loam are above average, the red dotted line. Sandy loam actually is the highest with 0.759, much higher than any of the rest. Now coming to the concerns that was raised about the bare soil. What if the high correlation in sandy loam was just because there were more bare soil samples? If that was true, then the bare soil bar should be the highest, or at least much higher than the vegetated soil. But actually the bare soil is around 0.495, and surprisingly the vegetated soil is a bit higher at 0.552. That's actually the opposite of what we would expect in remote sensing, because the bare soil should give the strong result, but here the vegetated sample is actually slightly better, not too much but slightly better. And neither of this is actually anywhere near the sandy loam. And it's also good to look at SAR band. The L band is performing a bit better than C band, but still even the best L band correlation is less than what we see for the sandy loam. So in real world, like bare soil always doesn't guarantee SAR signal. That's what this plot tells. If there is bare soil, nobody bothers them irrigating them. And if it is dry, then the radar backscatter can be very weak to the moisture changes. So that might be a reason. So irrigation also played a role here. Maybe the backscatter has an optimum soil moisture for good signal to noise ratio. When the soil is extremely dry, we have too much noise. And if it is bare soil, maybe it was not irrigated. But the difference is not that great, but still the bare soil is less than the vegetated soil in terms of correlation. So now we will see the next, we will further break down the actual proportion of bare soil and vegetated samples within each soil texture, and also look at the mean leaf area index. Maybe the sandy loam had very young plants with less leaf area index. That could be also a reason why we are seeing it. It may not be due to soil texture. That was another concern raised. So let's also see the leaf area index. And okay, so now we are looking at what's going on within each soil texture. On the left, I'm showing the mean leaf area index for each texture, and on the right, I'm showing the percentage of vegetated soil versus the bare soil. So if the high performance of sandy loam was because of weak vegetation, we would expect its mean LAI to be very low, but that's not the case. Sandy loam's mean leaf area index is 1.72, which is actually higher than clay, and sandy clay loam, and only lower than loamy sand. And sandy loam definitely had substantial vegetation cover, and it was nowhere near the bare ground. That's what LAI plot, and here on the right hand side we see that the 70% it is vegetated and only 30% it was bare. And loamy sand was 100% vegetated, and we see different distributions. More or less it's around 60 to 70%. All the soils are always vegetated, and so the distribution is more or less similar. And also loamy sand, even though it was fully vegetated, we saw a very high correlation, but the high correlation did not translate into a high R square when we ran the machine learning model. So what does it mean is that exceptional correlation and high random forest R square is cannot be explained by weak vegetation or having more bare soil. It's not due to vegetation in the sandy loam. That's what we see here. Why sandy loam is performing better? Maybe it's due to intrinsic physical properties of sandy loam itself, or due to some sort of dielectric response, surface roughness. Maybe these factors make SAR backscatter much more sensitive to moisture changes. So what I wanted to do is that I wanted to go one step further, not just compare the generic random forest model with the texture specific models, but also see what happens if we split the data by SAR frequency band, L band versus C band, or by land cover, bare soil versus vegetation soil. So each of these subsets I trained a separate random forest model. The table here shows the R square and RMSE for each of these models, along with the number of samples that we had. So what you see is the generic model with all 677 samples had an R square of 0.45, but the sandy loam, the specific model that was trained on sandy loam, only that model achieved a higher R square than the generic model of zero point 0.6, and the rest of the soil texture was far below that, which is not shown here in the table. This was the best performing model, and if we look at the model splits by SAR band, the L band and the C band only, their R square was actually 0.2 or 0.17, much lower than the generic model and nowhere near the sandy loam result. And if we split, most importantly the land cover split, the bare soil actually gives only 0.25 R square, and also the vegetated soil is 0.19. Again, both of these actually is worse than the generic model, and of course it's much lower than the sandy loam. So what it means is that even though we had good number of sample for both bare soil and vegetated soil, the model performance was not good. So one could argue that a sandy loam had more samples, but vegetated soil and bare soil also had uh, more samples. So this means that simply splitting the data by the radar band or land cover does not lead to better prediction for the random forest. And there is something really special about the sandy loam. So whatever the message that I gave in the previous video is still holding good. Maybe if you ask me the reason, there could be some possible reason. Maybe it is related to the physical property of sandy loam, like how radar waves interact with the soil's dielectric property or its surface roughness. This may just happen to be the optimal condition for predicting soil moisture for this particular region, for the Berambadi watershed. And so maybe in another region, say in North Karnataka, where our project is also collecting, different groups are collecting new data with different crops and irrigation practices. There we have more clay soil, black soil. So there we might see different result actually. Factors like rainfall, irrigation timings, crop type, all this play a role. What we see from this table is that for this data set and for this region, Berembadi, what we see is that sandy loam is a very sweet spot for the random forest soil moisture prediction using the satellite backscatter. We need actually more data from more places before we can say that this is a universal fact. For now, this is really an interesting result, I think, and a useful insight for operational soil moisture monitoring in the regions with similar condition. So as we get more data in the future, maybe we will be able to test whether these patterns hold, or maybe if other soils start to show better performance under different conditions. So thank you once again for watching this video. I would like to acknowledge Professor Sekhar Muddu and the Reward project, which actually supported and funded my data collection and this entire analysis. I also wanted to thank Mr. Soundar Rajan, who was the project associate within the Professor Sekhar Muddu's team, who actually worked with me to collect all this data in 2022 to 2023. Thank you again.